This question is from GATE Mechanical Engineering of 2014. This is question number 41 of set 2. The question is, a spherical balloon with a diameter of 10 meters shown in the figure below is used for advertisements. The balloon is filled with helium whose gas constant is 2.08 kilojoule per kilogram Kelvin at ambient conditions of 15 degrees Celsius and 100 kilopascal. Assuming no disturbance due to wind, the maximum allowable weight in Newton of balloon material and rope required to avoid the fall of the balloon is, also the gas constant of air is given, that is 0.289 kilojoule per kilogram Kelvin. Let's understand the force acting on this balloon. Since this balloon is filled with helium, it will have a buoyant force in the upward direction. Let's write FB. And this buoyant force is the weight of air removed by the helium. Okay, so in this space, whatever the air was there, so it is replaced by helium. So due to that, there will be a buoyancy force in the upward direction. Now, the helium is also having weight. This volume of helium will also be having some weight. So let's write W for the weight of helium, and let's write F for the maximum allowable weight of the balloon material and the rope required to avoid the fall of the balloon. Okay, now since this balloon is in equilibrium, so we can write FB must be equal to W plus F. Okay, and we need to find the value of F, so F will be equal to FB minus W. Now FB is equal to mass of air into the acceleration due to gravity minus W, weight of helium, will be mass of helium into acceleration due to gravity. So this is also equal to density of air into volume of air multiplied by acceleration due to gravity minus density of helium into volume of helium, okay, whatever the volume of helium is there, into acceleration due to gravity. Actually, this V and VHE, this volume of helium, will be same, because FB we are writing, this V belongs to the force buoyant force, and buoyant force is because of only this volume of helium. Okay, so this is the amount of air also replaced by the helium. Therefore, this V and VHE will be equal. So let's write the final equation here. So F will be equal to rho A minus rho helium multiplied by density of air minus density of helium multiplied by the volume of this balloon into acceleration due to gravity. Now we need to find rho A, that is the density of air and density of helium. So from ideal gas equation, we know that pressure times volume is equal to mass into gas constant into the temperature. So from here we can also write mass by volume, that is equal to density, is equal to P upon RT. Using this equation we can find the density of air, this rho A, and the density of helium. So let's find density of air. Density of air will be pressure of air divided by R, the gas constant of air, into the temperature. Now the pressure is 100 kilopascal. 100 into 10 to the power of 3 kilopascal divided by the gas constant of air. The gas constant of air is 289 joule per kilogram Kelvin multiplied by the ambient temperature of the air, that is 15 degrees Celsius. So 15 degrees Celsius, so we'll add 273. So this will be 15 plus 273 is 288 Kelvin. So from here we'll get the density of air is equal to 1.2014 kilogram per meter cube. Now similarly we can find the density of helium. So let's write here, density of helium will be equal to the pressure 100 kilopascal divided by the gas constant of helium, that is 2080 joule per kilogram Kelvin multiplied by the temperature 288. So this value will be, the density of helium is 0.1669 kilogram per meter cube. Now our main aim is to find the value of F, this value. So let's find it here. F is equal to rho A minus rho helium. So rho A is 1.2014, the density of air minus the density of helium, whole multiplied by V, the volume, right? And so the volume of this sphere will be 4 by 3 pi r cube, 4 by 3 into pi into r. Now the diameter is 10 meters, so r will be 5 r cube, 5 cube into the acceleration due to gravity. So 9.81 meter per second square. So from here we'll get F is equal to 5313.71 Newton. Okay, so let's fill in the blank. Therefore, the maximum allowable weight of balloon material and rope required to avoid the fall of the balloon is 5313.71 Newton. For more information, you can refer to the NPTEL course, lecture number 13, Buoyancy, on Fundamentals of Fluid Mechanics for Chemical and Biomedical Engineers by Dr. Raghavendra Gupta of the Department of Multidisciplinary at IIT Guwahati.